I'm Anil Kumar. Welcome to my website, Global Math Institute. In this video, we'll see how matrix can be utilized for performing linear transformations. We'll consider the solutions to following examples. We'll first talk about basic concepts, and then we'll find matrix which can perform these operations, which are reflection in the x-axis, reflection in the y-axis, projection in the x-axis, projection on the y-axis, enlargement about origin of a scale factor k stretch parallel to x-axis of scale factor r, reflection in the line y equals to x, and reflection in the line y equals to minus x. So basically, in this video, we'll learn strategy to write a matrix. So basically the question will be write a matrix to perform given transformation. So we'll begin with the very basic concept and then we'll move forward from there. So when we are saying linear transformation, what in general we can think about is a point on a coordinate plane, right? Let's say this is the coordinate plane where we have a point P and the coordinates are xy. Now because of the transformation, let us assume that this point has moved to some other position q. Right? And let the coordinates of this point be x1, y1. We need to find the transformation matrix which can do this operation. Perfect. That's what the idea is. So the steps involved are kind of like this. First step is write the position as a column vector. You can say as a column matrix. So we'll actually write this position not as xy in the form given, but as in a column xy. And in that case, if the matrix is M, then in that case the matrix M times this xy will actually provide us with the solution for the new position x1, y1. You get an idea. So that's the basic concept. So in this, what we'll have here is M is a transformation matrix. And that is the image. Perfect. So that is what we are trying to work out. So we are trying to figure out this transformation matrix which can be multiplied to the given point taken as a column matrix. Right? So in this particular case, we are also considering examples in 2D, 2 dimensions. Right? So we are considering the point xy. Now whenever you have a 2-dimensional transformation, then the matrix will actually be of the form is a square 2 by 2 matrix. Perfect. And for solving all these questions, what we are going to do here is consider a convenient point And the most convenient points to consider are a point here which is 1 0. So let me write this as a column, matrix 1 0, and the point here which is 0 1. So when you consider these points, in that case, their transformation using the matrix M will actually provide you a shortcut method to find the matrix which can perform the given transformation. Correct? So that is the concept here. So let us see how to apply this concept for the given examples. So in the very first case, we have reflection in the x-axis and reflection in the y-axis. So let us consider what happens when you do reflections in x and y-axis. So let's take both the examples side by side. As I said, we'll consider the points which are these 2 points, right? So on the x and y axis, the y-intercept unit away, correct? So this point here is 0, 1, and the point here is 1, 0. Right, so we are going to consider these points to write down the transformation matrix. This is 0, 1, and that is 1, 0. Now in first case, we're trying to perform the transformation. Let's call this as A. We want reflection in the x-axis. Now if you do that, reflection in the x-axis, then as far as this point is concerned, it just remains here. It doesn't move, right? It is on the x-axis, and the other point moves to a new location which is there. And what you get here is a point which is actually 0, minus 1. So that is reflection in the x-axis, right? Let me write down x and y on the axis also. Correct? So what we observe here is that the point, the first point, which was the x-intercept 1, 0, remains as such. So we can write down this as a part of our transformation matrix 1, 0. The new point which we get by transforming the y-intercept is 0, minus 1. So if I write 0, minus 1 here, and then if we take any point xy, then we'll see that it can perform a transformation which is reflection in the x-axis. So whenever you do reflection in the x-axis, the y value becomes negative. So in general, this will be the x value remaining same and the y value becomes negative y. So in our case, the matrix which can perform this transformation is 1, 0, 0, minus 1. Is that clear to you? So if you multiply 1 times x is x plus 0, right? And here 0 times 0 is 0, and minus 1 times y is minus y. So that you get, and that is the result which you expect when you do reflection on the x-axis. Correct? Now let's look into this once again when we talk about reflection in the y-axis. So we'll do part B here, and we'll now again consider reflection, but this time in the y-axis. So when I do reflection in the y-axis, then what happens? If I have a coordinate point x, y, then the transformation actually is that the y value remains same, but the x becomes negative. So what you get here is negative x and y. Now when we are trying to write down a matrix to describe this transformation, the first step is to consider them as a column matrix, right? So what we can do here is, see how I'm now working in the reverse fashion. So what we can do here is, we know that the point x and y is to be transformed, and what we need is minus x, y, correct? And what we need to find is the matrix, 2 by 2 matrix, which can do this transformation. Is that clear to you? Which we can find by our test points. So these are the test points. Reflecting on the y-axis, this point here comes on the side, and what we get here is minus 1, 0. And therefore, we get minus 1, 0 as the first column of our 2 by 2 matrix. The other point, 0, 1, just remains there since it is on the y-axis. So the final position is 0, 1, and there you go. So clearly, we easily got our transformation matrix M this time, which is minus 1, 0 and 0, 1. And that can do the reflection in the y-axis. Does it make sense to you? Did you see how simple it is once you understand the logic? You could verify the result by multiplication. That is, if I multiply, you will see minus 1 times x is minus 1, 0 times y is 0, so we get this. Perfect. And 0 times x is 0, and 1 times y is y. So by multiplying, you can verify the result. And that becomes the matrix which will describe a reflection in the y-axis for any point in 2D. Is that clear to you? Perfect. So I hope the strategy is absolutely clear. We'll really move forward now and answer the balance, other questions. Now what we have here is projection in the x-axis and projection in the y-axis. So let us now again try to understand the situation. So the points which we will be considering once again will be 1, 0 and 0, 1 for both the positions, right? Is that clear? Now in the first case, I'm trying to consider projection in the x-axis. So when we say projection in x-axis, let's call this as C. In that case, what will happen? The point 1, 0, 1 will come here, right? That is the projection on the x-axis. Is that clear? And the other point, it will remain on the x-axis itself. So once again, let's follow this strategy which we learned. We actually want, in general, any point xy, but if it gets projected, then what happens? Then the value of x remains same, but the value of y becomes 0. Is that clear to you? So therefore, we need a matrix M which, when multiplying any coordinate xy written in the form of a column, should give me the result as x0. That's what we are looking for. And this matrix M is what? So if I do the projection of 1, 0, I do get 1, 0 itself. And therefore, it is 1, 0. That is the first column. And for 0, 1, we get 0, 0. So that becomes the second part, second column. Do you see that part? And very easily, we do get our matrix which will describe this transformation where we could do projection in the x-axis. Is that clear? Perfect. So the matrix involved is 1, 0, 0, 0. Perfect. you can multiply and verify the results. Now let's do the next one. Now in this case, we are looking for a projection of a point, let's say somewhere here, which is xy. And we're talking about now D, which is projection in the y-axis. That means the coordinates xy will now be projected here, and what we get here is the x value becomes 0, right? Y value remains same. So that is the kind of transformation which we are looking for, correct? So let us put this in the matrix form. So what we need here is that the point xy should now become 0y, and we are looking for the matrix M, and that is the question. Find the matrix which can do this kind of a transformation. Now what we observe is that the matrix should be the coordinates of the point 1, 0, when you project them on the y-axis become 0, 0, right? So they come here and this becomes 0, 0. So the matrix here will be, the first column will be 0, 0. As far as the y intercept 0, 1 is concerned, it remains the same, and therefore that will be 0, 1, and this becomes your transformation matrix. Is that clear to you? So it is as simple as that, right? So, and we can write any general point. We use these two as our test points, and what you're going to get here is always 0, y. Since 0 times 0, x plus 0 times y will be 0, and 0 times 0 plus 1 times y will be y. So you can always check it out. Is that clear? Now let's look into the next example, which is enlargement. So we're talking about two things here. One is enlargement about the origin by a scale factor k. So let me describe this. So if I take a point which again is 1, 0, and 0, 1. So enlargement by a scale factor about the origin, right? So that means about this point by a factor of k. So that means scalar multiple of k, right? So if you do scalar multiple of k, this point will be at k0, correct? And on this side, this point will be at 0k. And therefore, you can definitely write down the matrix which can perform this operation. Perfect. So this time, let's write down our answer directly. So what we get here is k0, 0k, right, on any point xy will give us the result, which will be what? Now, if I consider a general point, let us say we have a general point xy here. And if I enlarge this by a factor of k, then what happens? We get a new set of points which will be kx, ky, correct? So here what we get here is kx, ky, correct? Or k times xy, correct? Which is same as k times xy, right? You can verify clearly, it makes sense. It is a unit vector, unit matrix multiplied by k, correct? So when you do this operation, it works. It does make sense to you, right? So in general, any enlargement of this form by a scale factor of k can be written in this form, right? I hope that makes sense. Now let's talk about the second case when we are taking stretch parallel to x-axis of scale factor r. Now what does that mean? So the first case which we considered here was enlargement about origin, scale factor k, correct? This is what we did. And now what we are thinking about doing is stretch parallel to x-axis. Now what does that mean? Let's consider our general points, test points 1, 0 and 0, 1. So when I say stretch factor of r, factor r, correct? In that case, we are doing stretch factor. So if I have a point xy, for example, if I have a point xy, then we are stretching this parallel to x-axis. So what we get here is the x value remains same, but the y becomes r times y. That is the whole idea. Perfect. So for our test points, this point here, when you multiply, what happens? It becomes 0r. That is the stretch factor, right? When you are only stretching in that direction. Perfect. Now if you have a point here, and if you are stretching parallel to x-axis, in that case, the x value will remain same, right? So the x value remains 1 and y value will be r times 0, right? So this value still remains the same. Perfect. And therefore, what should be the matrix? Well, clearly, in this particular case, the matrix should be 1, 0, 0, r. For any position xy, which will be transformed, and what you get is x, r, y. Is that clear to you? So you can perform the multiplication to test the result. But I hope you're getting the point, how this simple method helps you to write down the transformation matrix, correct? Now here is the last example for you. I will like you to take this as a test, right? So what we need to do here is to write matrix to perform given transformations. Right? So take your time, pause the video. First is the reflection in the line y equals to x. So we have reflection in the line y equals to x. The other one is reflection in the line y equals to minus x. Correct? So I hope you got the result. Now here is how we are going to look into it. So let me first sketch, right, and then we'll write down the transformation matrix. You can verify the results. So what we are given here is a line y equals to x which goes diagonally increasing, right? We need to do reflection on this line. So if I'm given a point which is test point 1, 0 and the test point 0, 1, what really happens if I do this reflection, this goes to that position on the line y equals to x, and what we get here is 0, 1. And on the other hand, this point comes to this position, and what we get here is 1, 0. Perfect. So looking into this particular transformation, we can now write down the transformation matrix. Moving 1, 0 to 0, 1 means really the first column will be 0, 1 and the second will be 1, 0. For any point x, y. And the reflection is actually interchanging x to y and y to x, right? So this is what you get. Perfect. So if we have a point, let us say, if we have a point on this side, let us say any general point xy, when you reflect it, it will become yx. Perfect. So that is the kind of transformation which takes place when you reflect in the line y equals to x. Does it make sense to you? Right. This is our line y equals to x. So I hope that is absolutely clear. And similarly, y equals to minus x will be a line which will be going downwards diagonally. So that's your line y equals to minus x. Now, here what is really happening is that if I have a point, let's use our test points, 1, 0 and 0, 1. If I reflect these points on the given line, what really happens? This comes on this side and the point really becomes 0, minus 1. On the other hand, that point moves on this side and what we really get here is minus 1, 0. So the transformation matrix clearly is 0, minus 1, minus 1, 0 for any point xy. And when you do the transformation, what you really get here is 0 times x is 0, minus 1 times y is minus y. And when you do minus 1 times x, you get minus x, and that is what the transformation is. Does make sense to you? Perfect. So I hope you understood the whole concept. How easily we could actually write down the transformation matrix for all the given cases. Now in another part of video, we'll consider the combination of these transformations. We'll also consider transformation of line segments. I hope that makes sense. And then we'll move on to the rotations. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.